Physics has long struggled with a profound gap: how chaotic, probabilistic quantum mechanics at the microscopic scale translate into smooth, stable classical reality. The traditional assumption is that extracting a definitive measurement from a quantum system requires isolating it from its environment to preserve fragile states. But biological tissue is warm, wet, and relentlessly noisy. Maintaining perfect quantum isolation in a living cell is practically impossible, because thermal jitter rapidly destroys delicate quantum superpositions. Frameworks like orchestrated objective reduction attempt to locate quantum computation inside neural microtubules, but they face immense biophysical hurdles against these strict thermal limits. If living systems are navigating this quantum to classical handoff, they must be using an operational mechanism that doesn't rely on perfect, long-lived quantum coherence at all. Defining this alternative mechanism is the primary obstacle to explaining how classical stability arises within a living system. Ido Margolin's theoretical framework, the transition law, offers a direct, testable blueprint for this handoff. It proposes that the global microbiome, along with the epithelial tissues of host organisms, forms a continuous planetary boundary layer, a living measurement field. This dense biological layer acts as a distributed swarm prism. It funnels countless isolated quantum sparks into a small set of stable macroscopic bands that physiological systems can process. The theory focuses on the physical constraints of the living boundary, moving away from explanations centered on vitalism or consciousness-driven wave function collapse. It functions as an operational interface principle, providing a computable bridge between physical laws and biological informatics. By treating the global microbiome as a distributed biological computer, the transition law shifts the burden of measurement from a metaphysical observer to the physical geometry of the boundary itself. This architectural sequence breaks down into 4 strict stages: spin, signal, gate, and tempo. It begins with the spin phase. Here, weak environmental drivers, like photons or magnetic fields, modulate the reaction yields of isolated microscopic chemical channels. A specific testable example is blue light striking a cryptochrome molecule, generating spin-correlated radical pairs, where weak magnetic perturbations bias the chemical outcome. These microevents are then encoded by the biological field in the signal phase. The local microbiome reacts collectively by emitting structured streams of volatile organic compounds, metabolites, and aerosolized cells. These mesoscale emissions form a spatial temporal data field, acting as a carrier system that transmits the initial quantum bias outward. The ambient microbiome successfully takes transient probabilistic physical inputs and converts them into a durable biological data stream. That data stream then encounters the gate operator, the physiological boundaries like the skin or mucosal layers that selectively filter the incoming signals. This boundary performs deco-engineering, utilizing macro-boundary geometry to replace the need for microscopic quantum coherence. The mechanism utilizes topological levers, like Mobius-like microboundaries in cellular structures. This operates as a formal cause. Physical geometry strictly constrains biological information flow. Traversing this single-sided loop yields a precise phase inversion for the transported signal. This inversion generates a robust interference by boundary effect, where signals interact to refine the incoming data. This interference narrows the acceptable biological response bands, allowing the tissue to function like a mesoscale interferometer. Proposed biological substrates for this topology include helical microvilli, chiral ciliary bundles, and twisted biofilm scaffolds. Unlike delicate quantum superpositions, this structural biofiltration is inherently resilient to the thermal noise of a living system. Structural biology dictates the act of measurement, utilizing geometry to funnel countless micropossibilities into a finite set of classical outcomes. The sequence concludes in the tempo phase, which establishes strict write-lock windows. Physiological systems parse filtered information in discrete, low-complexity phases to prevent overwhelming the host. These biological write windows, such as sleep consolidation rhythms or attentional phases, lock the selected signals into a permanent behavioral state. This formal coordination law governs the entire translation process. The central variable is MSIG, a composite microbiome index that tracks airborne cell density, viability, and ice nucleating particles. The transition law requires a positive, monotone coupling between this index and physiological flux. As MSIG increases, the strength of the translation must follow. The model also dictates a dose lag grammar. To validate the effect, physiological responses must manifest according to a stable 0 to 21-day delay following the environmental drive. Within this grammar, the model predicts superadditive responses, where concurrent environmental hazards interact to produce a multiplied impact on the host. This transforms abstract decoherence into a biologically parameterized apparatus that can be strictly audited and computed. Because the math focuses on boundaries, it scales upward. In an individual, translation operates through the gut-brain axis to bridge cellular reactions to neural states. At a regional level, aerobiome plumes dictate how hazards interact and coordinate across ecosystems. On a planetary scale, the entire living biological layer functions as a single, distributed macro-optical boundary prism across the Earth. To remain a rigorous framework, the transition law requires strict empirical falsification. The theory fails if there is no positive monotone coupling between MSIG and the boundary flux, if the 21-day lag grammar is absent, or if inert controls reproduce the same topology signals. A final check is the decoupling test. If classical trajectories persist unchanged when the microbiome is artificially suppressed, the hypothesis breaks down. Any bridging of physics and biology must survive these hard audits. Historically, quantum mechanics has often been interpreted as requiring a conscious observer to define a measurement. The transition law adopts an instrumentalist stance, viewing quantum measurement as an operational relation enacted by physical living structures. The global microbial field is non-conscious, yet its continuous filtering and gating perform the data coarse-graining required to stabilize a classical timeline. By time-stamping biosignals within specific write windows, the microbiome acts as a physical chronometer, aligning distret signals into a sequence that dictates macro history. This biological coordination establishes the stable classical environment that is absolutely required for complex nervous systems, and eventually conscious experience, to fully function.